All right, hi everyone. My name's Jutin, and today I'm going to be presenting a circuit modeling system that I've been working on for the past 6 months or so. This system is based on wave digital filters, or WDFs, which is a circuit modeling paradigm that lets you build circuit models out of discrete models of individual circuit components and their connections. So for example, let's imagine that we have a RC low-pass filter circuit like the one you see here. And in this circuit, we have three components. We have a resistor, a capacitor, and a voltage source. And all three of these components are connected to each other in series. Now, with wave digital filters, we can represent this circuit in kind of this tree structure. So this is what we see here. And in wave digital filters, the tree is kind of shown with the root at the top, which might seem a little backwards, but that's typically how they do it. And so at the root, we have this input voltage source, and then we have our series adapter, and then the two kind of leaves at the bottom of the tree are our resistor and our capacitor. So the nice thing about wave digital filters when you're trying to put together a circuit model in software, all you need is some code that can do some work for each one of these boxes, and then in your model you just have to route some waves in between these boxes, and that's your full circuit model. So some of the early wave digital filter software implementations, like this RTWDF library, they do that using kind of an object-oriented approach where you have a resistor class and a capacitor class and a series adapter class, and these are all part of this template hierarchy, or sorry, polymorphic hierarchy, and so you can put together your circuit at runtime using runtime polymorphism. And that works great, but you have this problem where the runtime polymorphism creates some performance bottlenecks that actually have a pretty big impact on these types of circuit models. And I gave a talk about that maybe 4 or 5 years ago now for the Audio Programmer YouTube channel, and I'll put a link to that below. So a few years ago, I was working on writing my own circuit modeling library, and I started out in a pretty similar way to RTWDF using this polymorphic hierarchy, but then eventually I figured out that I could get better performance using template metaprogramming. So that's what we have here. So basically, the way this works is each circuit component object gets put together in this template hierarchy, and now everything is known at compile time, so the compiler can optimize through a lot of things, and you get a lot better performance, but still not the best possible performance. I still wasn't totally happy. You still have a bit of computational overhead, and where that comes from is that we're still kind of doing things in a bit of an object-oriented way, in the sense that you have this resistor that represents kind of the resistor in your circuit, and you have all this data that is associated with the resistor, some impedance values, wave variables, that kind of thing. And all of that data, whether you need it or not, is going to be attached to this object and is going to persist for the lifetime of the object. So, you have these constraints around data layout and the lifetime of your data that you might want to be a little more flexible if you were to be able to do kind of the best, most performant implementation of this circuit model. So then a couple years ago, my friend Dirk wrote this great library called WD Models for the Faust programming language. And with WD Models, you write your circuit model in Faust. It looks a little bit like this. And then you use Faust to generate code or generate bytecode, or there's different ways to compile your Faust, but it's basically a code generation system that generates the code that actually does the circuit modeling. And this approach still has a few limitations, at least the way it works in Faust. So I wasn't quite able to get some of the performance that I wanted out of these models, but I really like the idea of this code generation approach. And so that's kind of the way that I went with this new system that I'm going to present here. So this system basically has three parts. There's a circuit description language, a code generation system, and a circuit component library. So we're going to go through it in that order. So to start, let's go back to our diagram of the RC low-pass filter that we had here. So basically what we want is a way to represent this circuit schematic in text. And so that's what we have here. We have our voltage source, our series adapter, and our resistor and our capacitor, kind of in the order that they appear as you go down the tree. Then we tell the circuit model that this Vin is our input, so the voltage source is going to be our input. And then we want to tell the circuit model that the voltage over our capacitor C1 is going to be the output. We could also do current instead, or we could take the voltage off of any other circuit component, that kind of thing. And right now we have all of these component values specified as basically compile time constants, but if we wanted to, we could make them things that are controllable at runtime. So we could do something like that. And now this is going to be a runtime variable that you set. So now we're ready to do our code generation, and we're going to do that using a tool called the WDF Compiler here. And the way this works is you give it your text representation of the circuit, and it's going to generate some code that will implement the circuit model for that circuit. So let's see what it looks like here. So first we have these three data structures. The params data structure is for kind of these user level parameters, so basically the component values. The impedances struct is for basically the circuit model's internal parameters. And then the state struct is for the model state. And so the way to think about this, the reason why we're splitting up these data structures in this way is that only the state data structure needs to persist for a long time. Everything else you can kind of generate on the fly whenever you need it, and so that gives you as the programmer a lot of flexibility for how you're gonna store this data and how you're gonna use it, and so that can help you to get better performance. Then we have two methods. First, we have this calc impedances method, and what this is going to do is basically you take in your parameters and your sample rate, and it'll generate your impedances struct. And then for your process method, this is going to compute basically one time step of your circuit simulation. Now you'll notice that right now everything is being generated with single precision floating point data types, but we could change that if we want. So we could do D-type double, and this will generate double data types instead, so you have a bit of flexibility there. And we also support generating code using the Jai programming language, so let's do that. And here we see basically the same thing, just written in Jai instead of in C++. For right now, we only support C++ and Jai, but we might support other languages in the future as well. So most of the basic circuit components and adapters are supported by the compiler by default. So that's your resistors, capacitors, series and parallel adapters, all of that. But there's a handful of things that either need some customization or you kind of want customization for them. So for example, here we have a diode clipper circuit. And when you're implementing diodes or diode pairs, you sometimes want to use some math approximations to speed up the computation that you're going to do. But the accuracy that you need from your approximation is going to depend on your specific use case, on the circuit and on the thing you're using the circuit for. So the way that we implement diodes in this system is as a custom component. So you have a custom component, and then you give it all these arguments that basically forward to your custom implementation. And here we see the custom implementation. And this is provided by the component library. And kind of the default thing is to use this fourth order approximation of the right omega function. But you could imagine that if you maybe wanted better performance and you didn't require this much accuracy, you could use a lower order approximation to do that kind of thing. Now for circuits with R-type adapters, we do something similar. So with R-type adapters, you typically need a specifically designed R-type adapter for your circuit. So again, it's a custom component, and you forward all of this stuff that you implement in your custom R-type adapter. And we provide some helper functions. So basically all you need to do is provide your scattering matrix, and then everything else is going to be handled for the most part by the helper functions. So the reason that we go to all this trouble to do all this code generation stuff and to give you this flexibility with custom components and so on is really for performance reasons. So here we see a performance comparison between WDF Compiler and a few of these other frameworks and systems that you might use. And you'll notice that the WDF Compiler implementation is usually the fastest, so here the smaller number is faster. We can look at this a little bit deeper as well. So here we have basically the time per sample that each model needs to process one sample, the number of operations or instructions per sample, the cycles per sample, which is what we just saw in the last chart, and then the instructions per cycle. And what you'll notice here is that the WDF compiler implementation usually has the fewest operations per sample, which means that we're doing a good job of cutting down on computational overhead. However, it doesn't always have the best operations per cycle. In fact, it's usually kind of at the lower end of how many operations per cycle it's doing. So that means that we could probably improve things a bit more by figuring out how to generate our code in a way that makes better use of the CPU pipeline. So that's something for us to look at in the future. Now, one of the reasons why some of the WDF libraries that use runtime polymorphism have a little bit of an advantage is that they allow you to construct your circuit model at runtime. So if you want to kind of build your circuit model on the fly, you're able to do that. Whereas with compile time and code generation systems, you're a little bit more limited. You're kind of fixed with whatever your circuit architecture is at compile time. But we can still do something to kind of get the best of both worlds using this hot reloading system. So what we have here is we have a plugin, and the plugin is going to watch this file here. And whenever we change this file and save it and so on, it's basically going to trigger the plugin to regenerate circuit modeling code for this file, and then it's going to compile that code into a dynamic library that the plugin can load and use to process the incoming audio. So, we could mess with this in real time here. We can change this component value, or we could change this to a, maybe this is an inductor instead. I don't know if that's going to do too much here, but yeah, we can mess around with this circuit. We can even add a parameter that you can use in the plugin to control one of the component values here. So I think that's right. So now we have this slider, and we can use it to change the value of our resistor. And I should mention that this is all using the JAI code being generated by the WDF compiler. And the reason for that is that JAI compiles really quickly. So here we're able to get a full kind of round trip here in well under a second. And this could probably be improved even more with a little more effort here. This is just something that I've thrown together kind of quickly. One more thing that I wanted to show is another little fun experiment I've been messing with, which is using WDF compiler in Compiler Explorer. And this is a local build of Compiler Explorer. I don't think that I'm going to try to upstream this or anything like that. But what we can do is we can put together a little circuit description and then immediately see, what's the output here. Like if we, change this to a parallel adapter, how's that going to change our modeling code? It's going to change some stuff down here probably. Or let's go back to series. But one of the fun things that we've been doing to further improve performance is figure out ways to kind of reduce some of these circuit elements. So for example, the compiler is automatically going to convert this RC series connection into a single circuit component that it can emulate with less computation. We can turn this off using a compiler flag here. So now the compiler is going to generate more code. This is going to take a little bit more computation to run. But if we just use the default behavior, then we get less code and it'll run a little bit faster. So that's all that I have to share for today. If you want to check out the WDF compiler or the prototyping plugin, there's going to be links to GitHub repos for both in the description of this video. You can download the WDF compiler from the releases page here and mess around with it for yourself. For the prototyping plugin, you're going to need to have access to the JI compiler to be able to use it. So if you're in the JI beta program, then give it a try. If not, you might have to wait a little bit. If you do want to use WDF compiler, definitely check out the tests folder here. There's a whole bunch of circuits that I've been using for testing, so there's probably some useful things in there that I haven't gotten around to documenting yet that you might want to look at. And yeah, I should say that I've been using this system for the last couple months here, both for some personal projects and for some commercial projects, and I've seen some pretty good results, so I'm pretty excited about how it's working at the moment, and I have some more ideas for trying to make it better in the future, so definitely stay tuned. Yeah, thanks for watching, and hope you enjoy your day.